know that astronauts have a higher risk of developing kidney stones. And that is because while they're in the microgravity environment, a reduced gravity environment, their bones appear to turn over a lot more frequently. That means that they break down and reform and break down and reform more frequently than we do here on Earth. And so what happens is that when the bones break down, it releases a lot of minerals that are stored in the bone, like calcium, magnesium, and those minerals are filtered by the kidney, and they can actually cause kidney stones. A large number of astronauts have developed kidney stones after coming back to Earth. The concern is while we're in low Earth orbit, coming around the Earth on the International Space Station, if you have a kidney stone emergency, you could easily bring back an astronaut. The problem is if you are on your way to Mars or you're on a moon base, that becomes a challenge. It could put an astronaut out of commission. It could be life-threatening. So we have to develop a capability that does not require surgery, that does not require a urologist necessarily, and something that is lightweight, that doesn't introduce any radiation, because astronauts are already being exposed to additional radiation from cosmic rays and the solar particle events. And so ultrasound just fits the bill.
In the last couple of years, we have improved the twinkling signal on the stones to readily identify them and be more confident that we are looking at a kidney stone. A higher contrast image so that the borders of the stone don't splay out or smear. We get a nice crisp edge for measurement. And we're also actually looking at the shadow that is produced by a kidney stone and measuring the shadow, and we're finding at times the shadow measurement accurately reflects the size of the stone, much better than measuring the stone. It's very important to know the difference between a 3, 4, 5 millimeter stone. There's only a few millimeters difference, but it can make a large difference in how that patient is treated. With these improved detection tools and sizing tools, we feel that we are reaching a space where we can be as sensitive and specific as a CT.
We have a new technology called ultrasonic propulsion, and it uses the radiation force of ultrasound to move kidney stones. And this is a new application that the FDA has not seen before. And so we need to demonstrate that it is safe and effective for use in humans.
We've developed a technology called burst wave lithotripsy. It's a new experimental procedure that we think can be used to non-invasively fragment kidney stones so that patients can just pass these fragments out painlessly.
Many years ago, I was diagnosed as having idiopathic hypercalciuria, which has resulted in quite a burden of kidney stones over the last 30 years. And it's because of those kidney stones that I became a subject in your research study. There was no pain involved. I was asked to move into different positions to help with the visualization of the stones. I myself, as well as the other investigators in the room, had a chance to see the stones move from their initial position.
We tried the sound wave lithotripsy, and that didn't work for a variety of reasons, and so both required laser lithotripsy. And on the way in to do that with you, we decided to see whether or not the stone bumping with ultrasound would work and be able to have an A-B comparison. Being a research guy myself, I thought that was an interesting thing to do, and that's my history.
Did you have pain during the procedure?
No, there's almost no sensation at all. The only thing I recall was sort of just a warming sensation. And I think, there's so much money to be saved, so much inconvenience, by focusing on prevention. And whether you're a long traveler or a Mars, astronaut in the future, those are the extreme cases.
This idea that we could develop a lower cost outpatient or emergency room treatment that's totally different from what we do now could actually reduce the cost of care here on Earth.